Hello, dear students. We'll discuss today the theory of MOSFET. Okay. So we know the this MOSFET is the family of the transistors. So after the device we have started the journey of the diode, then in the semiconductor field we have discovered the uh, different types of the transistor. So actually all these transistors, if we classify. Generally, we are divided. Generally, we know that is the bipolar junction transistor and field effect transistor. And this JFET and MOSFET, this family under the FET family, junction field effect transistor and metal oxide semiconductor field effect transistors. Other also we know the triag and thyristor. Okay, so MOSFET sometimes also called IGFET. So today's our topic actually the MOSFET. This MOSFET is referred to as sometimes EGFET, already I've told. Okay, and this full form of the MOSFET is the metal oxide semiconductor field effect transistor. Okay, so this MOSFET is the commercially more important than the JFET since most devices are suitable for very large scale integration. The MOSFET is also important power device. MOSFET uh, can be there are two types. Generally, we know them. That is, we'll discuss here these two types semiconductor MOSFET device, that is enhancement MOSFET and depletion MOSFET. Enhancement and depletion both are again is the N-channel enhancement type, P-channel enhancement type, and the same thing, the depletion type MOSFET is the two types, N-channel depletion mode and the P-channel depletion mode or MOSFETs. Okay, so in the also you have given the there are different types of the symbol related the symbol about the that is the N-channel depletion, P-channel depletion, N-channel enhancement, and P-channel. This is the symbol representation that is given in the here. Next, actually, already you have know this is the field effect transistor MOS, MOS. Now, these MOSFET have been constructed with the various semiconductors such as silicon and gallium arsenide and with the different insulator like SiO2, Al2O3, silicon oxide, and L2O3, SiSO2 combination is most common in the systems. Okay, the basic structure of the P-channel MOSFET is shown in the figure. And in this figure, actually, we have given the depletion type MOSFET and the enhancement type MOSFET. Okay, so before that, the basic structure of the P-channel MOSFET is shown in that is, that it consists of the lightly doped N-type semiconductor substrate into the two heavily doped P region. Okay, sometimes this will be called the N channel. Now, what is the P channel? When the P channel is the that is the when N-type semiconductor substrate into the heavily doped P channel substrate, then this is called the P channel. Now, if it is the N channel depletion, but here we have given the P channel depletion type MOSFET, and also we have given the that is the P channel enhancement type MOSFET. So this is our in our discussion. So before same thing, we know there were three terminals actually. Sometimes this MOSFET, if you go to the higher discussion, then you will go there are three terminal MOSFETs, four terminal MOSFET. Okay, so body have been considered. So here we'll mainly source, gate, and then these three terminal related this we will discuss about this. We'll applying the bias either source to gate or drain to source. Okay, so the yeah, next in this silicon dioxide, you can see here this after that the silicon dioxide is deposited on the that is the semiconductor bar, and then the metal has been deposited on the silicon oxide. So here, as the semiconductor and metal is considered as a two plate. Okay, and if you go to the naming is like that. If you start from the top position, so this will be the metal, then oxide, then semiconductor. So MOS, metal, then oxide layer, then semiconductor. So that's why the name is like that. Metal oxide semiconductor. As field effect means obviously the field will be affected. So mainly we know that they have given the four terminals. So but here mainly we discuss the three terminal MOS for that. Okay, the area of the gate metal together with the insulating oxide layer and the semiconductor channel produce a parallel plate capacitor. Okay, the SiO2 layer acting as a dielectric. As the gate is insulated from the channel by SiO2 layer, the device is termed insulated gate field resistor. The gate current of a MOSFET is much smaller than the JFET, since the insulating oxide layer offers a very high input resistance. Now, if we before to start the explanation of the this enhancement and depletion, obviously we'll discuss in details. So, but what is the comparison if we discuss? Since the electron mobility is larger than the hole mobility, and the N-channel device with a smaller area can achieve the same resistance as the P-channel device with a larger area. Okay, hence the N-channel MOSFET can have a smaller size than the P-channel counterparts. The N-channel devices are faster in switching applications. So N-channel MOS structure is more desirable than the P-channel structure. Okay. So now, if we discuss the what is the basic thing difference between the enhancement and depletion. So here, if you observe depletion layer, extra N type channel we have deposited. Okay, extra N channel we have deposited here, but near of the no N channel depleted in the enhancement type. No channel is there. The arrow is given, no channel is there for the enhancement type, but for the depletion, N type channel is here. Channel is available. Okay, extra in the fabrication process we have done. Okay, so this is the difference in the view point of view of the fabrications. Okay, so that's obviously we'll get the two different results for that. In the N type substrate, is grounded when negative voltage is applied, okay, to the gate. Positive charges will be induced on the N type. So N type will be induced on the semiconductor side due to the capacitor action. These positive charges being the minority carriers in the N type substrate produced on the inversion layer. Okay, producing the inversion layer. Okay. So an increase of the negative gate voltage enhance the induced positive charges in the semiconductor. These positive charges are the p-type carriers confined to a thin region called the channel. Below the oxide layer, if the positive voltage is applied to the source with respect to the drain, then the p-type carriers in the induced channel carry the current from the source to drain. Okay, the conductivity of the induced channel and hence the drain current is enhanced by the negative gate voltage. Hence the device is, so that's why as the channel will be increased. So as this is the name is the enhancement. Enhancement means increase. Okay. Now for the depletion, if we discuss what is the difference, if a portion of the semiconductor substrate, the portion, some portion of the substrate is for substrate between the source and the drain, okay, is diffused with the same type of impurity as that used for the formation of the source and the drain. And before the oxide layer, obviously, before the oxide layer is deposited. Okay. So the depletion MOSFET that is shown in the figure, you can observe when a positive charge is applied to the drain, if we apply the positive charges, the drain with respect to the source, a drain current flows from the zero gate to source voltage. That is VGS will be zero here. Okay. When the gate voltage is negative, positive charges are induced in the diffused N channel due to the capacitive action. The induced positive charges reduce the channel conductivity as a portion of the channel is depleted of carriers. The effective depletion of the majority carriers, that is the effective depletion of the majority carriers in the channel, justify the name depletion MOSFET. Okay, so this is the difference of that. Okay, as the induced in the diffuse change channel due to the capacitive action, the induced positive charge reduce the channel conductivity. A portion of the channel is depleted of carriers. The effective depletion of majority carriers in the channel justify the name diffusion MOSFET for the clearly the drain current falls as VGS made from negative. Okay, we can observe from that. So since the drain to source voltage is positive, as the drain to source voltage is positive, the voltage drop between the channel and the gate is greater near the drain than the near the source. Hence, the channel region near the drain is depleted more than near the source. Okay, so obviously, if you observe this phenomena, actually this phenomena in the analogous to the pinch of a JFET. Okay, so this is the actually happen in that state. So next we go to the next slide. So basically, these characteristics are basically low voltage device actually, as we know, and high voltage device are available for the up to the 600 volt, but with limited current, can be parallel. Okay, and quite easily for the higher current capability. Also, if you observe the that is the dynamic resistance, internal dynamic resistance between the drain and source during the on state limit the power handling capability of MOSFETs. Okay, and due to the very high losses of the high voltage devices due to the RDS will be on. And dominant in the high frequency application, actually get up in 100 kilohertz. This is the biggest application is in switch mode power supply. Okay, so also the already have that is the level that mainly consists of three regions actually, and the source gain drain, and the area labeled as the gate region is actually a sandwich during underlying the. So electrical charges of the current can flow from source to drain. This is the character depending on the charges applied to the gate. The semiconductor material in the source and the drain region are doped with a different types of material. Okay, so so that the NPN and PNP structure we can form. Okay, so what is the this is the most important if we application most important device in the digital system because as we know the this is the main application very good as a switching application which is the first in the digital application which are the gates these gates actually all the gates in the digital application fundamentals gate that is the depends on the switching application. So MOSFET we can use as a very good switch. Okay, obviously few parasitics that can be charges that can be occurred, but also nowadays there were good fabrications process and some very good modeling. We can eliminate these types of the parasitics charges, which will be created in the that is the metal silicon interlayer that is the oxide semiconductor interlayer at that position. Some trap charges also will occur into the silicon oxide. Okay, so these types of different types of parasitics charges may happen, but also for the very good sophisticated fabrication process, we can eliminate these types of these uh, elements. Also, this is the low power consumption, and uh, obviously, in the point of view of the devices, always you want this parameter low power consumption and the high intention integration density. Okay, that is very good for the packaging. And this is a very simple manufacturing method, and this is also stable, and this is economical for the large complex circuits. Okay, so another structure also is given for the N-channel MOSFETs. Okay, this is the both enhancement and depletion as we have given. And this is the 3D diagram you can observe. This 3D diagram MOS nowadays get is made on the mod silicon and channel length L and width W. In most these L is the length of the minimum feature size and W is the selected by the designer. But is connected to the ground to the NMOS to prevent the forward bias in the PN junction. Okay, there is the on state we have given S and D. When it is connected, this is the one, and when disconnected, this we call consider source to drain is not, this current is flowing, this is generally on state, no current is flowing, and this is the off state. Now also you can observe the characteristics of the in MOSFET. Depending on that, actually, there are two types of the characteristics we'll get. That is the VI characteristics, output characteristics, and the that is the another is the characteristics, drain current, and the VGS. Okay, that is the get to source voltage versus IDS and drain to source voltage versus IDS. So these two characteristics will get from here. Okay, so if we observe there will you can see uh, this is the this we can observe that is the sometimes current will be linearly increasing, then it will reach into the saturations. Okay, also you will go to the VGS and IDS if you that is the draw, then we see some it will be off, and after that it will be linearly increasing. Okay, so this is the same as the PMOS structure. Next, if we go to the same P MOSFET characteristics, so this is the depletion and the enhancement types we can accommodate into a single graph. Single graph means depletion modes and the enhancement modes we have drawn in the both. So previously we have seen here that is the when we are applying the minus 3 volt, minus 2 volt, minus 1 volt for the depletion and the for the enhancement. So actually what will be happen? Okay, so next as the figures you can observe here that is substantial drain current flows at VGS equals to 0, and VGS can be positive or negative in the form, but VGS is negative in the latter. Okay, so this drain current characteristics of an N-channel MOSFET which can be used in either the enhancement mode or the depletion mode. The positive values of the gate source voltage VGS produce the enhancement mode, whereas the negative values of the VGS result in the depletion mode. The transfer characteristics of the same MOSFET is indicated in the figure. Okay, and so sometimes we have seen the current is increasing when negative voltage from 0 it is the maximum for the depletion mode, but when we are increasing the negative voltage minus 1 minus 2 minus 3 for the VGS get to source voltage, then the current is decreasing, drain current is decreasing, and after that sometimes it will be very small. But for the enhancement this is the opposite. When we are applying the 0 voltage get to source voltage 0, then we are applying the positive voltage 0.5 1 point, so gate is so we have seen the IDS current is increasing. Okay, so from this is the switching application we can it can be performed. So what you can see in the depletion mode when VGS equal to 0, actually the transistor is the on condition, and certain minus 3 or minus 4 voltage it will be the off condition. So same thing enhancement when what we can about it, when 0 this is the off condition. Okay, when 0, this is the off condition, but when it will be increasing, this is the on condition. Okay, so these types of the two you can observe. And this is the static characteristics of the MOSFETs. Okay, uh, next, if we go to the switching mode of the models, so generally depending on this operation, performance operations or working principle, if we can make a table and it will get a logic level if we define that VDS equals VDD equals to 1, that is some voltage that is will indicate the 1, and VSS when it will count this will be 0, though we have seen when G equals to 0 for the NMOS this will be off, when G equals to 1 the gate equals to 1 this will be on condition. Okay, so same opposite for the PMOS. CMOS what will be when G get equal to 0, then it will be on condition. We can say from the operation when G equals to 1, this is the off condition. So from here, this is the switching application model of the MOSFET. Okay, so this is the main application of the MOSFET. Okay, and thank you. Thank you very much.